Now that we're going to start using reaction arrows to communicate all sorts of things like reagents and so on and so forth, I thought it would be worth describing how it is to interpret this language. So what we have on the left always is the starting materials, and what we have on the right is the products. That part's the easy part. But then all the reagents of interest end up going above the arrows usually, and below the arrows we tend to have things like solvent, time, and temperature. So someone who knows what they're doing would tend to look at this and say, okay, DJS ran a reaction starting with this 5-nitroindazole. He added to it the reagent PPTS and the reagent DHP. In order for him to figure out what's going on, that person would probably then translate those into images, and then those lead, after dissolving it in DCM, adding those reagents, and letting the reaction sit at room temperature for 3 hours, to this product. And again, if the organic chemist looks and sees a THP there, she would need to interpret the THP in order to figure out, hey, what is the overall structure? So there's certain acronyms you're just going to need to know. At the moment, DHP and THP won't be all that important, but PPTS and DCM you should definitely know. Okay, same idea here. This nitroindazole, in the case of my intern Ross running the reaction, he used PTSA, again something you should know, DHP, something I don't care if you know, and he ends up making this product using DCM. Heat, delta is a sign for heat. He was actually refluxing this reaction for 1 hour, and he ended up making that product. In the context of kinetic versus thermodynamic, the product that I made was kinetic. If you look at this structure, I attacked the nitrogen that's kind of more available. This is the kinetic product. By the way, it wouldn't be possible to know whether this is the kinetic product by looking at the reagents and reaction conditions unless you compare these two to each other. And though the time might signal to you that this is actually a slow process, I'm doing this at room temperature for 3 hours. Those are relatively mild conditions. This is a relatively fast reactions. Ross, on the other hand, ended up making the thermodynamic product the more stable product because he has the benzene ring there. It actually takes time for the THP to install first there and then migrate over, which is what actually happens in this mechanism. He ended up making the thermodynamic product. He heated it up and it was over in a hurry, but those were harsher conditions, a lot more energy available. This is the thermodynamic product because the product is more stable overall. This is the kinetic product because when I ran both reactions myself side by side, I noticed that this stuff forms first. That's why it's the kinetic product. It forms faster. This is thermodynamic product because it's more stable. Again, benzene ring versus not benzene ring. This is a more stable situation than this is. The moral of the story is reagents go above the arrow, solvents, time, and temperature. Those are the things that tend to go below the arrow. Okay, I mentioned that you should know PPTS and PTSA. What are they? PTSA stands for para-toluene sulfonic acid. If you look at this, you should recognize something that looks a lot like sulfuric acid. Therefore, you should recognize this as a very strong acid. pKa at least -2, if not more like -3, -5, somewhere in there. So very strong acid. In other words, this is partially why I called Ross's conditions the thermodynamic ones. Strong acid present, heat. These are much beefier conditions, more energy going in. Therefore, you can access the thermodynamic product. Meanwhile, PPTS stands for pyridinium para-toluene sulfonate. You have the same acid, but then you add in a base to buffer it. So this is a buffered system, much milder acid. So much weaker acid that I used versus Ross. Room temperature instead of reflux, as hot as it'll go. And that's the difference. Mine are the kinetic products. Mine are the things that form quickly. His are the ones that are more stable overall. Dichloromethane, of course, is 2 chlorines in a methane, otherwise known as methylene chloride. You should know that from lab. So dichloromethane is the solvent in both cases. And again, I don't care that you know DHP and THP, so I won't even bother to show you the structure.